Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Now, I want you to do something for me. Look down at your feet. Go ahead, I'll wait. Whether you're standing on carpet, concrete, or actual ground, I need you to imagine what's happening 400 feet beneath you right now. Because what I'm about to tell you is going to completely change how you see the world around you. Right now, as you're listening to my voice, there's a network pulsing with activity below you. It's older than the pyramids, more complex than the internet, and it's been operating in complete secrecy for millions of years. And here's the crazy part. Until 1997, we had absolutely no idea it existed. That's when everything changed. That's when a researcher named Suzanne Simard made a discovery that shattered every assumption we had about how nature works. And I mean everything. We thought forests were battlegrounds where trees competed ruthlessly for survival. We thought it was every tree for itself in a brutal fight for sunlight and nutrients. We were completely wrong. Picture this scene. It's the mid-90s, and Suzanne Simard is deep in the forests of British Columbia. She's a young forest ecologist, and she's got a hunch that nobody believes. While her colleagues are focused on what they can see, the towering Douglas firs, the spreading paper birches, Simard is obsessed with what's hidden underground. She's convinced that something extraordinary is happening in the soil, something that could rewrite our understanding of how forests actually work. So, she designs an experiment that sounds like science fiction. She takes radioactive carbon, completely safe, but traceable, and she feeds it to some trees. Not just any trees, but specific ones she's chosen carefully. Then she waits. She waits to see if her impossible hypothesis could actually be true. And you're not going to believe what she found. The carbon didn't stay in the trees she fed it to. Within hours it was moving, flowing, traveling underground through networks of fungal threads so thin they made spider silk look like rope. The radioactive signature lit up her equipment like a Christmas tree, revealing pathways that connected every single tree in the forest. But here's what made her heart race. This wasn't random distribution. The network was making choices. A mother Douglas fir wasn't just connected to her offspring, she was actively feeding them. Packets of carbon and nitrogen were flowing through living cables, traveling from the mature tree to her struggling seedlings growing in the shade below. This wasn't poetry or metaphor. This was measurable, traceable nutrition moving through fungal highways that stretched for miles underground. When Simard published her findings, the scientific community went into shock. Trees weren't competing. They were connected. They were collaborating. They were communicating. The forest wasn't a battlefield, it was a family. But that was just the beginning. Because once we knew what to look for, once we had the tools to trace these connections, the true scope of what we were dealing with became clear. And the numbers, when they started coming in, were absolutely staggering. Are you ready for this? In a single handful of forest soil, just one handful that you could scoop up with your bare hand, there lives more fungal network than there are stars in our entire galaxy. We're talking about over 100 billion connections. 100 billion in one handful of dirt. Think about that for a second. The device you're listening to this on, whether it's your phone or your computer, contains maybe a few billion transistors if it's really advanced. The human brain, the most complex structure we know of in the universe, contains about 86 billion neurons. But that handful of forest soil, it's running circles around both of them in terms of pure connectivity. Now, if that doesn't blow your mind, let me tell you about the largest living organism on planet Earth. You might think it's a blue whale, right? Those magnificent creatures that can grow to 100 feet long. Or maybe a giant sequoia, those ancient towers that touch the clouds. But you'd be wrong. The largest living organism on Earth is hiding in plain sight in Oregon's Blue Mountains, And it's not what you'd expect. It's a honey fungus. One single individual organism called Armillaria ostoyi, and it covers 3,600 acres. 3,600 acres. That's bigger than some cities. This single fungus weighs as much as 3 blue whales put together. And here's what should really keep you up at night. It's been growing continuously for at least 2,400 years. Some scientists think it could be 8,000 years old. 8,000 years. This thing was already ancient when the pyramids were built. It was mature when humans first figured out agriculture. It's been pulsing with life beneath our feet, making decisions and processing information for longer than recorded human history. But here's where this story gets truly wild, where it moves from amazing to absolutely mind-bending. These networks aren't just passively connecting trees like underground telephone cables. They're not just moving nutrients around randomly. They're making decisions, active, intelligent decisions about who lives and who dies. When Simard and her team started tracking those isotopes more carefully, following the chemical signatures through the fungal web, they discovered something that challenged our most basic assumptions about intelligence. The network was choosing which trees to feed and which trees to starve. It was playing favorites, and it wasn't random. Here's how it works, and this is going to sound like something out of science fiction, but it's happening right now in every forest on the planet. When a tree is dying, maybe it's been damaged by disease or insects or drought, e.g., something remarkable happens. Instead of hoarding its remaining resources, instead of fighting to the bitter end, that dying tree dumps its entire carbon reserve into the network. Everything it's stored up, everything it's worked for, goes into the fungal highways. Now, what happens next is where it gets really interesting. The network doesn't distribute those resources randomly. It doesn't just spread them evenly among all the trees. No, it makes strategic decisions. It feeds young seedlings that are struggling in the shade. It supports trees that are showing promise. It invests in the future of the forest. But, and this is crucial, it doesn't help everyone equally. The network can identify genetic relatives. It knows which trees are family and which trees are strangers, and it plays favorites accordingly. A mother tree will pour resources into her own offspring while letting genetically unrelated trees struggle on their own. Think about what this means. This underground network has a memory. It remembers previous interactions. It recognizes individuals. It makes complex decisions based on genetic relationships, health status, and potential for survival. It responds to threats by reallocating resources strategically. If you saw this behavior in an animal, you'd call it intelligence without hesitation. But we're talking about fungi, organisms that don't have brains, don't have nervous systems, don't have anything we traditionally associate with intelligence. Yet they're processing information on a massive scale, making survival decisions that span entire forests, and the evidence keeps getting stronger. Research published just last year has pushed us even further into territory that makes us fundamentally question what intelligence actually is. Scientists have documented fungal networks adapting their behavior based on past experiences. They've seen networks learning from mistakes. They've observed coordination between different fungal species, sharing information across what should be biological barriers. We're looking at something that operates like a vast, distributed intelligence. A billion-year-old network that processes information, makes decisions, and learns from experience. It's been operating beneath our feet this entire time, and we never knew it was there. Now, you might be thinking, okay, this is fascinating, but why should I care? What does this have to do with me? Well, here's the thing. This discovery isn't just changing how we understand forests. It's changing how we understand life itself, how we understand intelligence, and how we understand our place in the web of existence. Because if fungi can do this, if they can create planetary-scale networks that think and learn and make decisions, what else don't we know about the world around us? What other forms of intelligence are we missing because we're looking for brains and nervous systems instead of chemistry and connection? And here's what should really get your attention. We're just beginning to understand what these networks are capable of. Every new study reveals capabilities that seem almost magical. Networks that can solve complex problems, that can optimize resource distribution across vast distances, that can coordinate responses to threats in ways that put our best computer systems to shame. The forest floor beneath your feet isn't just dirt and dead leaves. It's the interface to a living internet that's been running for hundreds of millions of years. An internet made of flesh and chemistry, processing information at the speed of growth, making decisions that affect the entire planet. But that's just the beginning of this story, because what we've discovered about modern forests is nothing compared to what happened when fungi first inherited the Earth. 420 million years ago, in a world so alien I wouldn't recognize it as our planet, fungal spores landed on bare rock and began the most ambitious terraforming project in the history of life. They built towers that dominated empty continents. They dissolved mountains. They engineered the soil that everything else depends on. For 50 million years, they were the largest living things on land, and they used that time to fundamentally reshape the planet. And then, something happened that changed everything. The teachers created students who would surpass them. But the fungi didn't disappear. They didn't give up control. They just learned to rule from a different position. They learned to rule from below. That's where we're going next. To a time when mushrooms ruled the earth, when fungal empires rose and fell, and when the foundation was laid for the hidden kingdom that surrounds us today. Because to understand what's happening beneath your feet right now, we need to understand how this underground empire first conquered the world. And trust me, that story is going to change everything you thought you knew about who's really in charge of this planet. So let me take you back, way back, 420 million years ago, to a world so alien you wouldn't recognize it as Earth. Picture this: no grass beneath your feet, no flowers blooming in gardens, no trees casting shade on a summer day, no birds singing, no insects buzzing. The land is almost completely barren, just bare rocks stretching to the horizon, broken only by primitive moss clinging desperately to the waterline. This is Earth in the early Devonian period, and it's about to witness one of the most extraordinary transformations in the history of life. Because somewhere in what we now call Scotland, something remarkable is happening. A spore, no bigger than a particle of dust, is drifting on the wind. It looks insignificant, weightless, utterly forgettable. But this tiny spore is carrying a secret weapon that will change the world forever. It can dissolve rock. Now, I know that sounds impossible. How can something so small, something without muscles or tools or any apparent power, break down solid stone? Well, here's the beautiful thing about fungi. They don't need brute force. They have chemistry, and the chemistry they wield is so powerful, so precise, that it can turn mountains into soil grain by grain. When that spore lands on wet stone, it does something that no other organism on Earth could do at the time. It begins to grow. Fungal threads, thinner than human hair, start spreading across the rock surface. But these aren't just sitting on top of the stone, they're boring into it. They're releasing acids and enzymes that literally eat the rock, dissolving minerals and creating tiny cracks that spread and deepen with each passing day. And as this process continues, something extraordinary emerges from the landscape. Structures begin to rise from the dissolving bedrock, tall, imposing spires that dwarf everything else on the prehistoric landscape. These are the Prototaxites towers, and they're about to become Earth's first skyscrapers. Picture walking across this ancient world and suddenly seeing them looming ahead of you. Fungal monuments 24 feet tall and 3 feet wide. That's the height of a 2-story building, but they're not buildings. They're living organisms. Single, massive fungi reaching toward the sky like organic towers. For 50 million years, 50 million years, these fungal spires were the largest living things on land. Think about that timeline for a moment. 50 million years of fungal dominance. These structures were already ancient when the first dinosaurs appeared. They rose and fell, lived and died, for longer than mammals have even existed, and they were everywhere. Paleontologists have found their fossils on every single continent: Antarctica, Australia, North America, Asia. Wherever they look for rocks from this period, they find evidence of these towering fungi. But here's what's really wild about this story. These prototaxites weren't just growing randomly. They were engineering the planet. Every tower that rose from the bedrock was doing more than just existing. It was actively transforming rock into something new, something that had never existed before in Earth's history. It was creating soil. Now, this might not sound revolutionary to you. Soil seems pretty basic, right? It's just dirt. But here's the thing. Before fungi figured out how to make soil, life on land was essentially impossible for anything larger than moss. There was nowhere for roots to grow, no reservoir of nutrients, no medium for complex plant life to take hold. The continents were vast, sterile wastelands. The fungi changed all of that. Tower by tower, spore by spore, they were breaking down the geological foundation of the planet and rebuilding it into something life could actually use. They were the original terraformers, reshaping an entire world to suit their needs, and they were incredibly successful at it. For those 50 million years, the prototaxites ruled unchallenged. They grew larger and more numerous. They spread to every landmass. They dominated the landscape so completely that if you could have stood on Earth during this time, you would have thought you were looking at a planet of mushrooms. But then, around 370 million years ago, something strange happened. These massive fungal empires that had dominated the land for epochs suddenly vanished. Not gradually, not slowly declining. They disappeared from the fossil record almost overnight. What happened to the rulers of the ancient world? Here's the plot twist that nobody saw coming. The fungi had created their own competition. By spending millions of years breaking down rock into rich, fertile soil, they had inadvertently solved the one thing that was keeping complex plant life from colonizing the land. They had created the perfect growing medium for their own replacements. It's one of evolution's greatest ironies. The teachers had created students who would surpass them. Plants began to flourish in the soil that fungi had spent eons creating. They grew larger, spread faster, and started to compete for the same resources that had sustained the fungal towers. And plants had an advantage that fungi couldn't match. They could harvest energy directly from the sunday. Now, you might think this is where the fungi exit the story, defeated by their own success. But you'd be wrong, because fungi are nothing if not adaptable, and they came up with a solution that was so elegant, so revolutionary, that it became one of evolution's greatest success stories. They made a deal. Picture this negotiation happening in slow motion over millions of years. Plants had what fungi needed, sugar captured from sunlight. Fungi had what plants needed, access to water and minerals locked away in the soil and rock, so they struck a bargain that would reshape life on Earth. The terms were beautifully simple. Plants would share their sun-captured sugar with fungal partners, and in return, fungi would provide water, minerals, and protection from pathogens. This partnership, called mycorrhiza, became one of the most successful collaborations in the history of life, and the results were immediate and spectacular. Within 50 million years, a blink of an eye in geological terms, forests covered the continents. Plants that had struggled to survive on bare rock suddenly exploded in size and diversity. Every major plant family that successfully conquered land did so with fungal partners attached to their roots. But here's what's really remarkable about this partnership. It wasn't equal. The fungi never gave up their position of power. They just learned to exercise it more subtly. Instead of ruling as towering spires visible from miles away, they learn to rule from below, hidden in the soil, pulling the strings of their plant partners. Think about it this way. When you look at a forest today, what you're seeing is really just the visible part of a vast fungal plantation. The trees, the bushes, the flowers, they're all connected to and dependent on fungal networks underground. The farmers live below ground, and what we see above ground are essentially their crops. And the numbers prove this. When researchers use ground-penetrating radar to map forest root systems, they make a discovery that still shocks people when they first hear it. Up to 70% of a forest's living biomass is actually fungal. 70%. The trees we admire, the canopies we walk under, the green world we think we know, it's just the tip of the iceberg. The real forest, the majority of the living tissue, is underground. It's a vast network of fungal threads connecting every plant, processing information, moving nutrients, making decisions about who thrives and who struggles. The trees are just the visible interface of a hidden empire, and this empire remembers its roots. Remember those rock-dissolving abilities that built the first soil? Modern fungi never lost them. Even today, they're actively mining the earth, dissolving bedrock and extracting minerals that plants can't access on their own. They're still terraforming the planet, just more quietly than their towering ancestors. Here's something that will blow your mind. Scientists estimate that fungi move over 13 billion tons of carbon through soil systems every single year. 13 billion tons. That's more than the entire weight of all land animals on Earth combined. They're not just living in the soil, they're actively cycling the chemistry of the entire planet, and they're still growing those partnerships that saved them from extinction. Today, 90% of all plant species depend on fungal alliances. 90%. From the tiniest wildflower to the mightiest redwood, almost everything green on Earth survives because of deals struck with underground partners. The few plants that have managed to break free from fungal control had to evolve chemical warfare to do it. Plants like mustard and cabbage produce compounds specifically designed to poison fungi and break free from their networks. But even these rebels pay a price. And not, they tend to be shorter-lived, more vulnerable to disease, and require more fertilizer when we try to grow them. Most plants chose a different path. They embraced the partnership so completely that they can't survive without it. If you take a tree seedling and try to grow it in sterile soil without fungal partners, it will struggle and often die, even if you give it all the water and nutrients it should need. The partnership has become so fundamental that plants have essentially outsourced their root systems to fungi. But fungi didn't stop there. They kept innovating, kept evolving new ways to influence and control their environment. And some of those innovations are so sophisticated, so precisely targeted, that they border on science fiction. They learned to manipulate not just plants but animals. They figured out how to control behavior, rewrite instincts, and turn other organisms into unwilling servants. That's where our story goes next. Into the realm of mind control, biological puppetry, and fungi that can literally take over other organisms and make them dance to fungal rhythms. Because if you think partnerships with plants were impressive, wait until you see what fungi can do when they decide cooperation isn't enough. In the depths of rainforests around the world, a different kind of fungal control is playing out. Not partnership, not mutual benefit, but complete and total domination. And the precision with which they execute this control is absolutely terrifying. Deep in the Amazon rainforest, something absolutely horrifying is happening right now. An ant is walking along a familiar trail, following the same path it's taken hundreds of times before. But today is different. Today, something is terribly wrong. The ant stops mid-stride, its antennae twitch erratically. Its legs seem unsteady, uncertain. For the past 3 weeks, something has been growing inside its body, something that shouldn't be there. Ophiocordyceps unilateralis, a fungus with a name as sinister as its purpose. and it's been very, very patient. For 21 days, this fungus has been living as a hidden passenger inside the ant's body. It's been consuming non-vital organs, carefully avoiding anything that would kill its host too quickly. It's eaten through fat reserves, muscle tissue, even parts of the circulatory system. By now, it's consumed roughly 30% of the ant's body mass. But here's the terrifying part. The ant has been walking around, going about its daily business, completely unaware that it's being eaten alive from the inside. But the fungus hasn't just been feeding, it's been preparing, growing specialized structures, producing chemical compounds, getting ready for the most sophisticated act of biological manipulation ever documented. Because now, having reached critical mass inside its host, Ophiocordyceps unilateralis is ready to take control. What happens next defies everything we thought we knew about the boundaries between organisms. Chemical compounds flood the ant's brain, MDC, not destroying it, not killing the ant, but reprogramming it. The ant becomes a passenger in its own body, watching helplessly as something else takes the wheel, and the precision of what happens next will absolutely blow your mind. The infected ant doesn't wander randomly. It doesn't stumble around confused. Instead, it begins to climb with mechanical precision to exactly 25 centimeters above the forest floor. Not 20 centimeters, not 30, 25. This height isn't arbitrary. It's the perfect elevation for spore dispersal, where air currents are optimal and the humidity stays precisely where the fungus needs it. But it gets even more specific. The ant doesn't just climb any plant. It seeks out a leaf on the north-northwest side of vegetation, where humidity levels remain between 94 and 95% throughout the day. The fungus has essentially programmed GPS coordinates into the ant's brain, and the ant follows them with robotic obedience. Then comes the final act. At solar noon, when the sun is directly overhead and conditions are perfect, the ant performs what scientists call the death grip. It clamps its mandibles, its jaws, onto the main vein of the leaf with such force and precision that the bite penetrates deep into the plant tissue. Now here's what should absolutely chill you to the bone. Paleontologists have found fossilized leaves from 48 million years ago to 48 million years ago that show identical bite marks. This isn't some recent evolutionary development. This precise mechanical behavior has been refined and perfected across geological time. The fungus has been programming ants to perform this exact same death grip for longer than mammals have dominated the earth. But the fungus isn't done. Once the ant has clamped down on that leaf vein, Ophiocordyceps does something that seems almost impossibly cruel. It dissolves the ant's jaw muscles. The ant is now permanently locked in place, unable to move, unable to escape, unable to do anything but serve as an anchor point for what comes next. Within hours, a stalk begins to emerge from the ant's head. It grows slowly, but inevitably, bursting through the exoskeleton like some nightmare plant sprouting from the ant's skull. And within days, this stalk begins to rain spores down onto the trails below, where healthy ants continue to walk, completely unaware of the microscopic death sentences drifting down from above. Now, you might think this is just one horrifying example from a single species, but you'd be wrong. This isn't unusual behavior for fungi. It's practically standard, operating procedure. In 2018, researchers made a discovery that shows just how sophisticated this biological puppetry has become. Different species of Ophiocordyceps have evolved to control specific ant species with surgical precision. Each fungus produces a unique cocktail of mind-controlling compounds that only works on its intended target. It's like having a key that only fits one lock, except the key is made of chemicals and the lock is a living brain. When scientists tried giving the wrong fungus to the wrong ant species, FU, essentially testing whether these chemical keys were interchangeable, something fascinating happened. The fungus killed the ant without controlling it. It was like watching someone try to start a car with the wrong key. The engine might turn over, but it won't run properly. The puppet strings only work on the right puppet. Each species of ant has its own specialized fungal puppeteer, evolved specifically to hack that particular nervous system. We're looking at millions of years of evolutionary warfare, with fungi developing increasingly sophisticated biological hacking tools and ants evolving defenses that the fungi then learn to overcome. But insects aren't the only victims of this fungal mind control. Let me tell you about something that's happening right now in caves across North America. Something so devastating that it's literally erasing entire species from the continent. In the caves of the Pacific Northwest, millions of bats hang sleeping through the winter months. Their metabolism slowed to preserve energy through the long months when insects are scarce. They look peaceful, almost serene, suspended from cave ceilings in clusters that can number in the thousands. But many of them won't wake up in spring, because creeping across their wings and faces while they sleep is a fungus called Pseudogymnoascus destructans. And this fungus has figured out something absolutely diabolical. It doesn't kill the bats directly. That would be too simple, too quick. Instead, it grows slowly across their wings and facial tissues, creating irritation and inflammation. This forces the bats to wake up more frequently during hibernation, scratching at the infected areas, trying to relieve the discomfort. Each time a bat wakes up during winter, it burns through precious fat reserves. A bat that should sleep soundly for months starts waking up dozens of times, metabolic fires burning through energy stores that were carefully calculated to last until spring. The bats literally starve to death in their sleep, consumed not by the fungus directly, but by their own awakened metabolisms. The numbers are absolutely staggering and heartbreaking. Since 2006, white nose syndrome has killed over 6 million bats in North America. 6 million. Entire hibernacula that once housed thousands of bats now stand empty, silent tombs where thriving colonies used to echo with life. Some caves that researchers visited for decades, places where they could count on seeing certain species year after year, are now completely lifeless. Species that took millions of years to evolve, that filled crucial ecological niches, are disappearing in the span of a human generation. And here's what makes this even more terrifying. The fungus is still spreading. It's moving across the continent like a silent plague, reaching new bat populations every year. Scientists are frantically trying to develop treatments, but they're essentially racing against extinction. But perhaps the most chilling aspect of these fungal puppet masters isn't what they're doing now, it's how quickly they're getting better at it. Laboratory studies have revealed something that should keep every biologist awake at night. When researchers expose pathogenic fungi to new host species in controlled environments, the fungi can evolve effective control mechanisms in as few as 10 generations. 10 generations. With some fungal species producing new generations every few days, that means we're watching evolution happen in real time, adaptation occurring faster than we can study it. Think about what this means in practical terms. A fungus encounters a new host species, IM, maybe through climate change, bringing them into contact, maybe through human transport mixing ecosystems that were previously separated. Within weeks or months, that fungus can develop the chemical tools necessary to manipulate its new host. We're not just dealing with static biological weapons that took millions of years to evolve. We're dealing with rapidly adapting systems that can develop new forms of biological control almost as fast as we can identify them. It's like fighting an enemy that learns from every battle and comes back stronger each time. And the scope of fungal manipulation goes far beyond what I've described. Researchers have documented fungi that control the behavior of beetles, making them climb to optimal spore dispersal locations before dying. There are fungi that manipulate spiders, causing them to weave special webs designed to protect developing fungal fruiting bodies. There are even fungi that control other fungi, parasitic species that hijack their relatives and turn them into spore-producing zombies. Each case reveals new levels of sophistication, new ways that fungi have learned to hijack the biological machinery of other organisms. They can rewrite instincts that took millions of years to evolve. They can override survival behaviors that should be hardwired into their victims. They can make organisms act against their own interests with mechanical precision. The more we study these interactions, the more we realize that fungal control might be far more common than we ever imagined. How many animal behaviors that we think of as natural might actually be influenced by fungal manipulation? How many migration patterns, feeding behaviors, or mating rituals might have fungal puppet masters pulling the strings? Recent research has found that even plants can fall victim to fungal manipulation. Some fungi infect plant tissues and alter their chemical signals, making them more attractive to the specific insects that the fungus needs for spore dispersal. The plants essentially become unwilling advertisements, broadcasting chemical messages that draw in the exact vectors the fungus requires. We're beginning to understand that the natural world is full of puppet shows we never knew we were watching. Behaviors we thought were the result of evolution and instinct might actually be choreographed by hidden fungal controllers working behind the scenes. And here's what really should terrify us. If fungi can develop this level of control over other organisms, what happens when they turn their attention to us? We like to think that humans are somehow immune to this kind of biological manipulation, that our large brains and complex consciousness make us resistant to fungal control. But the evidence suggests we might not be as immune as we think. Throughout human history, we've been dancing with fungi in ways we're only beginning to understand, and some of those dances have been a lot more dangerous than we realized. From medieval villages consumed by madness to modern medical crises that are rewriting the rules of infection, humans have been part of the fungal story all along. We've just been too arrogant to realize how often we've been the ones being controlled rather than the ones in control. That's where we're heading next, into the dark history of human fungal interactions, where bread became poison, where visions shaped religions, and where the microscopic masters of manipulation first learned to influence the species that thought it ruled the world. August 3rd, 1345. The sun rises over the peaceful village of Pont-Saint-Esprit in southern France, and everything seems normal. People wake up, tend to their animals, prepare for another day of medieval life. Children play in the streets while adults go about their morning routines. By all accounts, it should be just another ordinary day in this quiet riverside community. But by noon, the village is drowning in madness. People are stumbling through the streets, screaming about tigers stalking them through their own homes. Neighbors are convinced they can fly, leaping from windows and rooftops with absolute certainty that they'll soar like birds. One man jumps from a second-story window, shatters both legs on impact, then continues running down the cobblestone streets, insisting to anyone who will listen that he's an airplane. Within hours, 300 people are hallucinating. Entire families are consumed by visions so vivid, so terrifying, that they can't tell reality from nightmare. People are tearing off their clothes, convinced that their skin is on fire. Others are seeing demons lurking in shadows, hearing voices commanding them to perform acts of violence. By the end of the week, 7 people are dead, and 50 more have been committed to asylums. The survivors will struggle with flashbacks and psychological trauma for years to come. What could cause an entire village to lose its grip on reality so suddenly, so completely? The answer lies in their daily bread. Hidden in the rye flour that formed the foundation of their diet was a purple-black growth that looked harmless enough. But this seemingly innocent fungal infection contained some of the most powerful psychoactive compounds known to nature. The villagers of Pont-Saint-Esprit had been poisoned by ergot, a fungus that produces chemicals nearly identical to LSD. Now, this wasn't the first time ergot had terrorized human communities. For centuries, outbreaks of what medieval chroniclers called street Anthony's fire had been sweeping through towns and villages across Europe, leaving trails of madness and death in their wake. The symptoms were always the same: burning sensations that felt like flames consuming the body from within, hallucinations so intense that entire communities would be convinced they were under attack by supernatural forces, and gangrenous limbs that would literally fall off without bleeding. People would wake up in the morning to find their fingers or toes had simply detached during the night, blackened by a circulation-destroying toxin their own food had delivered. Modern historians now believe that ergot outbreaks were responsible for some of the darkest chapters in human history. The witch hunts that consumed Europe and later Salem, the sudden mass hysteria that convinced entire communities that their neighbors were in league with the devil. Many scholars now think ergot contamination triggered these episodes of collective madness. Think about it. You're living in a small, isolated community where everyone eats bread made from the same grain supply. Suddenly, people start having vivid hallucinations, seeing things that aren't there, exhibiting behavior so bizarre that it seems supernatural. In an age before scientific understanding of psychoactive compounds, what explanation would make sense other than witchcraft or demonic possession? The Salem witch trials of 1692 and 1693 might have been the result of ergot-contaminated rye. The accusers described symptoms, convulsions, hallucinations, the sensation of being pinched and bitten by invisible forces that perfectly match ergot poisoning. And Salem was surrounded by rye fields that would have been particularly susceptible to ergot growth in the wet, cool conditions of that period. Even the French Revolution's Great Fear of 1789, when rumours of aristocratic conspiracies swept through the countryside and triggered widespread panic, coincided with reports of bread contamination. Entire regions convinced themselves that nobles were poisoning their grain supply, not realizing that fungi were doing the job quite effectively on pot, their own. For thousands of years, humans have been unwitting participants in a chemical dance with fungi, often without ever realizing we were dancing at all. But our relationship with the fungal kingdom goes much deeper than accidental poisoning. In fact, fungi might have shaped human civilization more than any other group of organisms. Let me take you back to ancient Sumeria, 6,000 years ago. Picture a warm day in one of humanity's first urban settlements. Someone has left a batch of barley gruel fermenting in a clay pot a little longer than usual. Maybe they forgot about it. Maybe they were just busy with other tasks. When they finally return to check on their food, they find it's changed. It smells different, looks different, and when they taste it, carefully, because food safety was literally a matter of life and death, they discover something that will change the course of human history. That first sip of accidentally concentrated alcohol was humanity's introduction to the transformative power of yeast, and we embraced it with enthusiasm that bordered on religious devotion. By 3000 BCE, Egyptian tomb workers were receiving daily rations of beer as part of their wages. Beer wasn't just a luxury, it was one of humanity's first workers' rights, considered so essential that it was literally carved into stone as part of employment contracts. The pyramids, those monuments to human engineering and ambition, were built on yeast. Workers received 4 to 5 litres of beer per day as standard rations. The alcohol provided calories, the fermentation process made the drink safer than water in an age before understanding of sanitation, and the nutrients from yeast supplemented their diet in crucial ways. But fungi weren't just helping us build monuments, they were helping us stay alive. Fermented foods became humanity's first preservation technology, allowing us to store nutrition through harsh winters and long journeys. Bread, cheese, wine, beer, all of these foundation foods of human civilization depend entirely on fungal processes. We didn't understand what was happening, of course. For thousands of years, fermentation seemed like magic. Grain and water would mysteriously transform into intoxicating beverages, Milk would become cheese. Dough would rise into bread. Ancient cultures attributed these transformations to gods and spirits, never imagining that microscopic fungi were doing all the heavy lifting. Then came September 28th, 1928, a moment that would save more lives than any single discovery in human history. Alexander Fleming, a Scottish bacteriologist, returned from a 2-week vacation to find his laboratory in London in typical post-vacation disarray. Petri dishes filled with bacterial cultures were stacked on his bench, many of them contaminated with various molds and fungi that had drifted in through open windows. Fleming was about to wash these contaminated plates down the sink when something caught his eye. One dish, growing Staphylococcus bacteria, had been contaminated by what looked like an ordinary green mold, but around the mold, something extraordinary had happened. The bacteria couldn't grow. There was a clear zone, a circle of death where no bacteria survived. Most scientists would have noted the contamination, discarded the plate, and moved on. But Fleming was curious. He isolated the mold and began testing it systematically. What he discovered was that this fungus, APS, later identified as Penicillium notatum, was producing a substance that could kill bacteria without harming human cells. That observation launched the antibiotic age. Within 20 years, penicillin was saving millions of lives annually. Diseases that had killed humans for millennia suddenly became treatable. Infections that would have meant certain death became minor inconveniences. Average human lifespan jumped by 8 years globally, almost overnight in evolutionary terms. Fleming had stumbled onto one of fungi's most potent weapons, their ability to wage chemical warfare against bacteria. For millions of years, fungi and bacteria had been locked in evolutionary arms races, each developing new weapons and defenses in an endless cycle of biological combat. Penicillin was just one arrow in a vast fungal arsenal that had been refined over geological time, and we thought we'd won. We thought we'd found the magic bullet that would end infectious disease forever. Medicine entered what many called the golden age of antibiotics, a time when doctors believed that microbial threats were essentially solved problems. But fungi remember everything, and they had been watching. By 1947, just 4 years after penicillin became widely available, the first penicillin-resistant bacteria appeared. The organisms that Fleming's mold had been fighting for millions of years were already equipped with defenses. They just needed time to deploy them. What followed was an evolutionary arms race played out in real time. We developed new antibiotics. Bacteria evolved resistance. We created stronger drugs. Fungi shared their chemical innovations with bacterial allies. Every weapon we borrowed from the fungal arsenal was eventually turned against us, as microbes learned to neutralize our borrowed firepower. And here's where the story gets truly frightening. We started to realize that we might be losing this war. Today, antibiotic-resistant infections kill more people annually than AIDS and malaria combined. Bacteria that were easily treatable just decades ago are now virtually immune to our most powerful drugs. But bacteria weren't the only microbes learning to resist our treatments. The fungi themselves were evolving too, developing defenses against the antifungal drugs we'd created to fight them. And unlike bacteria, fungi are eukaryotes, complex cells like our own. Drugs that kill fungi often damage human cells in the process, making treatment incredibly difficult. Then came the emergence of something that has infectious disease specialists around the world absolutely terrified. In 2009, in Japan, doctors identified a new species of yeast that didn't match anything in their medical textbooks. They named it Candida auris, and it would soon become one of the most feared pathogens on the planet. Here's what makes Candida auris so terrifying. It resists every antifungal drug we have. Every single one. Patients infected with this fungus face mortality rates of up to 60%, and there's essentially nothing we can do to help them. But that's not even the scariest part. The really chilling discovery came when researchers started analyzing the genetic makeup of Candida auris isolates from around the world. They expected to find evidence that the fungus had emerged in one location and then spread globally through travel and trade. Instead, they found something that defied explanation. Candida auris had appeared simultaneously on 3 different continents: Asia, Africa, and South America. The strains were genetically distinct, meaning they had evolved separately in each location. This wasn't one organism spreading around the world. This was parallel evolution, with fungi in different parts of the globe independently developing the same deadly capabilities. It was as if the fungal kingdom had collectively decided that now was the time to become untreatable, and multiple species had gotten the memo simultaneously. The implications are staggering. If fungi can independently evolve drug resistance in multiple locations at once, how many other species are on the verge of similar breakthroughs? And Candida auris spreads through hospitals like wildfire. Unlike most fungi, which require specific conditions to survive outside their hosts, this species can live on surfaces for weeks. It contaminates medical equipment, spreads through ventilation systems, and transfers between patients. Through the hands of healthcare workers, entire hospital units have been shut down and decontaminated, but the fungus keeps returning. The organism kills within 90 days of infection. It targets the bloodstream, spreading through the body faster than treatments can slow it down. Patients often don't realize they're infected until the fungus has already overwhelmed their systems. By the time symptoms appear, it's usually too late. What's particularly insidious is how Candida auris chooses its victims. It primarily targets people whose immune systems are already compromised: cancer patients undergoing chemotherapy, elderly people in intensive care, premature babies in neonatal units. These are the most vulnerable members of our society, people who depend entirely on medical care for survival. But the fungus isn't content with picking on the weak. Recent cases have shown it can infect healthy individuals too, particularly healthcare workers who spend time in contaminated environments. We're starting to see the emergence of community-acquired infections, cases where people with normal immune systems contract the fungus outside of hospital settings. And here's the really terrifying part. We have no idea what's driving this emergence. Why now? Why are fungi suddenly developing these capabilities? Why are multiple species simultaneously becoming resistant to our treatments? Some researchers believe climate change might be accelerating fungal evolution, creating new environmental pressures that favor drug-resistant strains. Others think our widespread use of antifungal agents in agriculture and medicine has created selection pressures that are driving resistance. Still others wonder if we're seeing the natural result of an evolutionary arms race that has been building for decades. Whatever the cause, one thing is clear: the age of easy victories over fungal pathogens is ending. We're entering a new era where fungi are fighting back with weapons we don't understand and can't counter. The organisms that gave us bread and beer and penicillin are reminding us that they're not just our partners in civilization, they're also our competitors, and they've been preparing for this competition a lot longer than we have. But the real question isn't what fungi have done to us in the past, or even what they're doing to us now. The question is what they're preparing to do to us in the future, because the evidence suggests that we're on the verge of changes that will make everything I've described seem like a gentle warm-up. The climate is changing. Fungi are evolving, and the thermal barrier that has protected warm-blooded animals for millions of years is beginning to crack. October 15th, 2013. A patient walks through the doors of Royal Brompton Hospital in London with what seems like a routine complaint: a persistent cough that won't go away. It's the kind of symptom that emergency rooms see dozens of times every day. Probably a lingering cold, maybe a mild case of bronchitis, nothing that a course of antibiotics can't handle. But this cough is different. It's been going on for weeks, getting progressively worse despite multiple rounds of treatment. The patient is increasingly tired, running low-grade fevers, struggling to catch their breath even during light activity. Standard bacterial cultures come back negative. Viral tests show nothing unusual. For days, the medical team runs test after test, looking for the usual suspects that cause respiratory infections. Then, someone thinks to test for fungi, and when those results come back, they chill the entire medical team to the bone. Aspergillus fumigatus, a fungus that's everywhere in our environment, floating through the air in every breath we take. Normally, it's completely harmless to healthy people because of one simple fact: it can't survive at human body temperature. Our 37 degrees Celsius creates a thermal dead zone where most fungi simply cannot function. It's been our species' shield against the fungal kingdom for millions of years. But this strain is different. This Aspergillus fumigatus is thriving at 37 degrees. It's growing, reproducing, and spreading through human lung tissue as if it were designed specifically for the job. The patient has become patient zero of something that should have been impossible: I-4 thermal evolution in real time. For 3 billion years, warm blood has been our evolutionary fortress against fungal infection. While fungi could colonize the cooler parts of our bodies, our skin, our nails, the spaces between our toes, they couldn't penetrate our core temperature. That 7-degree difference between our body heat and the ambient temperature where most fungi thrive was the difference between life and death, between health and infection. Think about it this way. Almost every fungal infection you've ever heard of affects the cooler parts of the human body. Athlete's foot between your toes, nail fungus on fingers and feet, ringworm on exposed skin. These infections stay on our periphery because our internal temperature creates a biological firewall that fungi simply cannot cross. Until now. What happened to that patient in London wasn't an isolated incident. It was the first documented case of something that researchers had been warning about for years. Climate change was about to breach humanity's thermal defense system, and the breach was happening faster than anyone had predicted. A landmark study, published in 2023, tracked 8,000 fungal species across 30 years of global temperature records. The results were absolutely terrifying. Fungi are adapting to heat 25 times faster than previous models had predicted. For every single degree of global warming, researchers documented 12 new species breaching the thermal barrier that had protected mammals since the dawn of warm-blooded life. Let me put this in perspective for you. Currently, about 4.5 million people die from fungal infections every year worldwide. 4.5 million. That's more deaths than malaria and tuberculosis combined. But here's the crucial detail. Almost all of those deaths occur in people with compromised immune systems, cancer patients, AIDS victims, people taking immunosuppressive drugs, the very old and the very young. Healthy immune systems have been able to handle the few fungi that could tolerate human body temperature. But what happens when that changes? What happens when a significant percentage of environmental fungi develop mammalian thermal tolerance? Computer models from Johns Hopkins University have run the numbers, and the projections are absolutely nightmarish. If just 5% of common soil fungi develop the ability to thrive at human body temperature, annual deaths could reach 50 million within 2 decades. 50 million people dying from fungal infections every single year. To put that in perspective, that's more than the total death toll of World War I. Every year, from organisms that most people have never even thought about as threats. And the evidence suggests we're already seeing the early stages of this thermal adaptation. Hospital labs around the world are reporting increasing numbers of fungal infections that don't respond to standard treatments. Strains that grow at temperatures that should kill them. Species showing up in body systems where they've never been found before. Meanwhile, our defenses against fungal infection are weakening with every passing year. Modern life, with its antibiotics that wipe out protective bacteria, its immunosuppressive drugs that treat cancer and autoimmune diseases, its air conditioning systems that create perfect fungal growing conditions, is creating opportunities that fungi have never had before in human history. Then came COVID-19, and everything got exponentially worse. During India's devastating second wave in 2021, hospitals were overwhelmed with coronavirus patients. Intensive care units were running at capacity. Steroids were being administered to critically ill patients to reduce inflammation, and medical oxygen supplies were being pushed to their limits. It seemed like the pandemic couldn't get any worse, but it did, because COVID-19 became a fungal multiplier. Mucormycosis cases exploded by 10,000%. 10,000%. A fungal infection that doctors might see once or twice in their entire careers suddenly became a daily reality in Indian hospitals. And this wasn't just any fungal infection, Macy Faye. This was one of the most aggressive, most destructive pathogens in the fungal arsenal. Mucormycosis, also known as black fungus, doesn't just infect people, it consumes them. It grows through facial tissues like acid, dissolving bone and cartilage as it spreads toward the brain. Patients would arrive at hospitals with what looked like severe sinus infections, but within days, the fungus would be eating through their eye sockets, their jaws, their skulls. Surgeons were performing operations that seemed to belong in horror movies rather than medical textbooks. They were removing eyes, cutting away portions of jaws, excising chunks of skull in desperate attempts to stay ahead of the fungal growth. Even with these radical surgeries, even with the most aggressive treatments available, half of the patients died anyway. The images coming out of Indian hospitals during this period were absolutely heartbreaking. People with half their faces surgically removed, trying to speak through the remaining tissue. Families watching their loved ones disappear piece by piece as surgeons raced against unstoppable fungal growth. But the human health crisis might actually be a sideshow compared to what's happening to our food supply. Because while we've been focused on fungi threatening individual lives, an even larger catastrophe has been quietly building in the fields that feed the world. Let me tell you about Magnapotha oryzae, a fungus with an innocent-sounding name that masks one of the most destructive agricultural pathogens on the planet. This organism causes wheat blast and rice blast, and it's currently staging a global conquest that threatens to starve billions of people. The fungus appeared in Brazil in 1985, wiping out wheat crops across the country's agricultural heartland. For decades, it remained a South American problem, contained by geographic barriers and climate differences. Agricultural scientists warned that if it ever escaped Brazil and learned to adapt to different growing conditions, the results would be catastrophic. In 2016, their worst fears came true. Wheat blast appeared in Bangladesh, 8,000 miles from its South American origin. Within months, it had destroyed entire harvests across the region. The same fungus that had terrorized Brazilian farmers was now loose in Asia, the continent that feeds more than half of humanity. But the fungus wasn't done traveling. In 2020, it appeared in Zambia, proving it could survive in African growing conditions too. Each new continent it reached brought new opportunities for genetic mixing, new chances to develop resistance to fungicides, new possibilities for evolutionary breakthroughs that could make it even more destructive. Here's what makes wheat blast so terrifying. It destroys crops overnight. Farmers can go to sleep looking at healthy fields and wake up to find their entire harvest blackened and worthless. The fungus produces spores that spread on the wind, infecting new plants faster than any containment effort can stop them. And no wheat variety shows meaningful resistance. Plant breeders have tried for decades to develop blast-resistant wheat, but the fungus evolves around their defenses almost as quickly as they can be deployed. It's like playing chess against the opponent who can see all your moves in advance and counter them before you make them. The same fungus already claims 15% of global rice production. 15% of the crop that directly feeds more than 3 billion people simply doesn't make it to harvest because of this single pathogen. In some regions, the losses are much higher. Up to 50% of rice crops in parts of Asia are destroyed by blast disease annually. But rice and wheat aren't the only crops under threat. Agricultural pathologists are watching with growing alarm as fungal diseases jump between plant species, learn to resist treatments, and spread to new growing regions with unprecedented speed. Coffee rust has already destroyed entire plantations across Central America, wiping out Arabica varieties that took decades to develop. Banana Panama disease is spreading through plantations worldwide, threatening the Cavendish variety that makes up virtually all commercial banana production. Citrus canker is devastating orange and lemon groves, while soybean rust reduces yields across the American Midwest. Each of these diseases represents millions of people whose livelihoods depend on crops that fungi are systematically destroying. But the real nightmare scenario isn't any individual crop failure. It's what happens if fungal pathogens successfully adapt to attack corn. Corn feeds a third of humanity, either directly through human consumption or indirectly through livestock feed. It's the foundation of food security for billions of people. If fungal diseases develop the ability to devastate corn crops the way they're currently destroying wheat and rice, global famine becomes not just possible, but probable. Agricultural models suggest that simultaneous failure of rice, wheat, and corn production due to fungal disease could trigger food shortages, affecting up to 2 billion people within 5 years. 2 billion people facing starvation because fungi learned to eat our food faster than we can grow it. And the evidence suggests this isn't a distant possibility, it's an approaching reality. Climate change is creating warmer, wetter conditions that favor fungal growth. International trade is spreading fungal pathogens to new regions faster than natural dispersal ever could. Modern agriculture, with its reliance on genetic monocultures, creates vast fields of genetically identical crops that fungi can exploit with devastating efficiency. We're essentially creating perfect conditions for fungal catastrophe, while simultaneously weakening our ability to respond to it. Agricultural research budgets are shrinking just as fungal threats are exploding. The number of plant pathologists studying these diseases is declining, even as the diseases themselves are becoming more complex and dangerous. Meanwhile, fungi are getting better at their job with each passing season. They're developing resistance to fungicides almost as soon as we deploy them. They're jumping between host species with increasing frequency. They're adapting to new climates and new growing conditions faster than we can track them. Some researchers believe we're witnessing the emergence of what they call superfungi, pathogens that combine the worst characteristics of multiple species through genetic exchange and rapid evolution. These hypothetical organisms would be resistant to all current treatments, capable of infecting multiple crop species, and able to survive in a wide range of environmental conditions. If such organisms emerge, and the evidence suggests they're already in development, they could render entire agricultural systems obsolete within years. Crops that have fed humanity for millennia could become impossible to grow commercially. Food security, the foundation of modern civilization, could collapse under fungal assault. But even that apocalyptic scenario might not represent the full scope of what's coming, because while we've been focused on fungi threatening our health and our food supply, something even larger has been building in the background. The planet itself is changing in ways that favor fungal dominance. Temperatures are rising, weather patterns are shifting, and the fundamental rules that have governed life on Earth for millions of years are being rewritten. And fungi, with their billion-year history of survival and adaptation, are positioned to be the biggest winners in this planetary transformation. What we're witnessing isn't just a medical crisis or an agricultural crisis. It's the opening stages of a fundamental shift in the balance of power on Earth. The kingdom that has ruled from below for so long is preparing to reclaim its position as the dominant form of life on the planet, and we're running out of time to figure out how to coexist with our new fungal overlords. Imagine this scene. Phoenix, Arizona, summer of 2045. The sun rises over a city transformed by 3 decades of accelerating climate change. The temperature gauge reads 55 degrees Celsius, ESR. That's 131 degrees Fahrenheit, ESR. And this is the 20th consecutive day of what meteorologists are calling hyperheat. The city that was once the symbol of human adaptability to desert conditions has become a testing ground for the limits of mammalian survival. But humans aren't the only ones being tested. In the early morning moisture that condenses on the superheated concrete, something stirs in the urban soil, something that wasn't there a generation ago, something that couldn't have survived in this environment just decades earlier. Cryptococcus gattii, once confined to the tropical regions of Australia and South America, is now thriving in the desert heat of the American Southwest. But this isn't the same organism that researchers catalogued in the 20th century. This version has learned a new trick during the warming years, an adaptation so sophisticated it seems almost impossible to believe. Instead of waiting passively for mammals to inhale its spores, this evolved Cryptococcus has developed the ability to actively hunt. It grows toward human settlements, following our carbon dioxide trails like a biological bloodhound. The fungus can detect the exhaled breath of sleeping humans from hundreds of meters away and will grow steadily toward that chemical signature, positioning itself for optimal infection when people wake and begin their daily activities. Now, before you dismiss this as wild speculation, let me tell you about some research that's going to fundamentally change how you think about fungal intelligence. In 2019, researchers at Duke University designed an experiment that sounds like science fiction, but produced results that are reshaping our understanding of what fungi can actually do. They took colonies of Candida albicans, MS, the same fungus that causes yeast infections, and exposed them to human body temperature in carefully controlled intervals. Remember, 37 degrees Celsius should be lethal to most fungi. It's been our thermal shield for millions of years. But within 50 generations, AT, just 50 generations, the fungi didn't just learn to survive at human body temperature. They began to prefer it. They had evolved not just tolerance but actual attraction to the conditions inside mammalian bodies. They were no longer trying to avoid human-level heat. They were seeking it out. But here's the part that should absolutely terrify you. When the researchers returned these heat-adapted fungi to cooler conditions and maintained them there for 100 generations, the fungi maintained their preference for human body temperature. Evolution had become memory. The fungi remembered their adaptation even after 100 generations of not needing it. This isn't just genetic adaptation. This is something that resembles learning in the way we normally think of it. These organisms developed a preference, retained that preference despite changed conditions, and could reactivate their heat tolerance almost instantly when exposed to warm conditions again. If that's not convincing enough that we're dealing with something far more sophisticated than we ever imagined, let me tell you how the interconnected nature of modern life is accelerating fungal spread at digital speeds. A contaminated shipping container leaves Mumbai at sunrise. Within 14 days, 2 weeks, it's being unloaded at the port of Los Angeles. Spores that were designed by evolution to travel inches, to spread slowly through local environments over decades or centuries, are now crossing oceans faster than most people take vacations. In 2017, a single batch of contaminated medical endoscopes spread drug-resistant fungi to 35 hospitals across 7 countries before anyone realized what was happening. By the time epidemiologists identified patient 0 in the Netherlands, patient 10,000 was already infected in a hospital ward in Singapore. We've created a global circulatory system that fungi are using like a highway network. International air travel, cargo shipping, medical tourism, food distribution, every connection that binds our world together has become a potential pathway for fungal dispersion. But the truly chilling realization is that we might not be fighting individual fungal species at all. We might be confronting something that operates as a collective intelligence, a planetary-scale network that processes information and makes decisions in ways we're only beginning to understand. Let me tell you about an experiment that Japanese scientists conducted that completely redefined what we thought was possible for organisms without brains or nervous systems. They took a species of slime mold, Tresh place, technically not a fungus, but closely related and exhibiting similar network behaviors, and placed it on an agar plate marked with food sources that corresponded to the locations of power. Tokyo's major subway stations. They wanted to see if a brainless organism could figure out efficient transportation routes. Within 26 hours, the slime mold had recreated Tokyo's subway system. Not approximately, not roughly, it had grown a network of connections that nearly perfectly matched one of the most sophisticated transit systems ever designed by human engineers. A system that took decades of planning, millions of dollars in research, and teams of transportation experts to develop was replicated by an organism with no nervous system in just over a day. The implications are staggering. If a simple slime mold can solve complex optimization problems that challenge human intellect, what might the vast fungal networks that span continents be capable of? What kind of information processing might be happening beneath our feet in networks that dwarf our most sophisticated computer systems? Recent experiments with fungal networks have revealed capabilities that seem to border on magic. These networks can maintain information flow even when 90% of their connections are severed. They're more resilient than the internet. They can respond to threats collectively, with fungi thousands of miles apart simultaneously changing their behavior in response to localized damage. Most remarkably, they appear to share chemical defenses across species barriers. When one type of fungus in a network develops resistance to an antifungal compound, that resistance can spread to completely different species through chemical communication. It's as if the entire fungal kingdom maintains a kind of biological internet for sharing survival strategies. Some researchers are beginning to whisper a heretical thought that challenges our most basic assumptions about consciousness and intelligence. What if intelligence isn't binary? Either you have it or you don't, but exists on a spectrum. What if we've been too arrogant, too anthropocentric, to recognize forms of intelligence that don't look like ours? Consider the evidence. Fungal networks process information across vast distances. They make complex decisions about resource allocation. They remember past experiences and modify future behavior accordingly. They coordinate responses to threats. They solve optimization problems. They learn and adapt faster than we can track them. If you observed this behavior in any animal, you would call it intelligence without hesitation. The only reason we resist applying that label to fungi is because they don't have the biological architecture we associate with thinking, brains, neurons, nervous systems. But what if that's like insisting that intelligence can only exist on silicon chips because that's how our computers work? What if fungal networks represent a completely different approach to information processing, one that's actually superior to animal intelligence in many ways? After all, fungal networks have been operating successfully for 1 billion years. They've survived 5 mass extinction events that wiped out most other forms of life. They've adapted to every environment on Earth, from the deepest ocean trenches to the frozen wastes of Antarctica. They've learned to manipulate the behavior of other organisms with surgical precision. Maybe the question isn't whether fungi are intelligent. Maybe the question is whether we're intelligent enough to recognize intelligence when it doesn't look like us. If this sounds like science fiction, consider what military strategists and computer scientists are already doing with fungal networks. The Pentagon has commissioned studies on using slime molds for battlefield logistics, recognizing that these organisms can solve supply chain problems faster and more efficiently than traditional computing approaches. Tech companies are experimenting with fungal computers, FCEBIF, biological processors that use chemical signals instead of electrical ones to process information. Early prototypes suggest that a fungal computer covering just 1 acre could match the processing power of a conventional data center while consuming nothing but sugar water. The catch, of course, is that we can suggest inputs to these biological computers, but we can't control their processing. The networks make their own decisions about how to handle information, what solutions to prioritize, what connections to maintain or abandon. We're essentially trying to harness a form of intelligence that operates by rules we don't understand, using methods we can't predict to solve problems in ways we never would have imagined. And that brings us to the most unsettling possibility of all. What if the current wave of fungal adaptation, ASP, the thermal tolerance, the drug resistance, the aggressive spreading, isn't random evolution responding to environmental pressures? What if it's a coordinated response by a planetary intelligence that's been watching us, learning from us, and preparing for the next phase of Earth's biological history? Think about it from the fungal perspective. For the past few centuries, humans have been reshaping the planet at an unprecedented pace. We've altered the climate, acidified the oceans, triggered the sixth mass extinction, and created conditions that favor rapid evolutionary change. From a fungal point of view, we might look like a planetary disturbance that needs to be managed, and fungi are masters of management. They've been regulating forest ecosystems for hundreds of millions of years, deciding which trees live and which die, controlling nutrient flows, maintaining biological balance on continental scales. What if they're simply applying those same management principles to the problem of human civilization? The evidence suggests that fungi aren't trying to destroy human civilization so much as compost what doesn't work and feed what does. They're offering us a deal, just like they offered plants 400 million years ago. Stop trying to dominate. Start learning to collaborate. The mycorrhizal networks that connect forest trees operate on principles of reciprocity, not exploitation. Trees that contribute to the network receive support during difficult times. Those that try to cheat the system get cut off from communal resources. It's a biological economy based on mutual benefit and long-term sustainability. Maybe that's the choice fungi are presenting to humanity. We can learn to participate in these ancient networks, contribute to the biological systems that have sustained life on Earth for billions of years, and benefit from fungal partnership the way plants have. Or we can continue our chemical warfare against organisms that have survived 5 mass extinctions, hope our thermal advantage holds as the planet warms, and gamble that beings who've had 1 billion years to prepare haven't anticipated our every move. The kingdom that rules from below has been patient. They've waited through ice ages and asteroid impacts, through the rise and fall of countless species, through environmental changes that would have wiped out less adaptable organisms. They can wait a little longer for us to make our choice, but the evidence suggests they won't wait much longer. The thermal barriers are falling, the chemical defenses are failing, the environmental conditions are shifting in their favor. The fungi are prepared for what's coming next, even if we're not. The question is whether we'll be part of their vision for the future of life on Earth, or just another layer in the compost pile of planetary history. Here's the plot twist that nobody saw coming. In 2022, mycologist Paul Stamets walked into a meeting at the Department of Defense carrying something that looked completely ordinary. Just a simple brick, the kind you might use to build a garden wall. But this wasn't an ordinary brick. It was grown, not manufactured. Made from mycelium, the thread-like structures that form fungal networks. Stamets placed that brick on the conference table and began explaining its properties to a room full of military engineers, stronger than concrete in compression tests, fire-resistant to temperatures over 1,000 degrees Celsius, self-healing when damaged, literally able to regrow missing sections if provided with basic nutrients. And here's the kicker. It could be grown from agricultural waste in just 7 days, using nothing more sophisticated than controlled temperature and humidity. By the end of that meeting, the Pentagon had ordered 1 million units. The fungal revolution had been quietly building for years, but suddenly it exploded into mainstream awareness. In 2019, fashion designer Stella McCartney debuted leather made from mushroom roots at Paris Fashion Week. The material looked, felt, and performed like traditional leather, but it was grown in laboratory conditions without harming a single animal. Adidas followed with athletic shoes made from fungal foam that provided superior cushioning while being completely biodegradable. IKEA announced plans to replace traditional furniture materials with mycelium alternatives that could be grown to exact specifications and would naturally decompose at the end of their useful life. By 2025, the global mycelium industry was worth $40 billion annually, and growing at a rate that traditional materials couldn't match. But building materials and fashion accessories were just the beginning. The real revolution was happening in places most people never see. Researchers at MIT were quietly programming fungal networks as living computers. They had figured out how to input nutrients in specific patterns and read chemical outputs one time, essentially creating biological circuits that could process information at the speed of growth rather than the speed of electricity. Think about what this means. A fungal computer covering just 1 acre could theoretically match the processing power of a slurry. A conventional data center, while consuming nothing but sugar water and producing oxygen as a waste product. No silicon mining, no rare earth elements, no massive cooling systems, no electronic waste that takes centuries to decompose. The catch, and this is crucial, is that these biological computers can't be controlled in the traditional sense. We can make suggestions by providing inputs, but the networks make their own decisions about how to process information. They don't just compute, they interpret, optimize, and sometimes ignore our instructions entirely when they identify better solutions. It's like having a research assistant who's brilliant but completely independent. You can pose questions and provide data, but you have to accept that the answers might not be what you expected, and the methods used to reach those answers might be completely beyond your understanding. And the applications are expanding faster than anyone anticipated. Fungal networks are being tested for traffic management in major cities, with early results showing they can reduce congestion by up to 30% compared to traditional computer-optimized systems. They're being used to optimize supply chains, design more efficient building layouts, and even predict market fluctuations with accuracy that surprises financial analysts. But perhaps the most revolutionary applications are happening in medicine, where fungi are providing solutions to problems that have plagued humanity for millennia. Psilocybin, the psychoactive compound found in what people call magic mushrooms, isn't just treating depression. Brain scans show it's physically rewiring neural connections, reversing decades of ingrained patterns within hours. Patients who have suffered from treatment-resistant depression for years are experiencing remission after single sessions with psilocybin-assisted therapy. The mechanism is extraordinary. The compound appears to dissolve the rigid thought patterns that characterize depression and anxiety, allowing the brain to form new neural pathways that bypass damaged or dysfunctional circuits. It's like having a biological reset button for mental health conditions that were previously considered incurable. Lion's mane mushroom extracts are regenerating nerve tissue in ways that neuroscientists thought impossible. Alzheimer's patients showing cognitive improvement after months of treatment. Stroke victims regaining function in damaged brain regions. The compounds in this fungus appear to stimulate the growth of new neurons and the repair of damaged nerve pathways. Turkey tail mushrooms are extending cancer remission rates by over 300% in clinical trials. The polysaccharides they contain seem to enhance the immune system's ability to identify and eliminate cancer cells while protecting healthy tissue from chemotherapy damage. Cordyceps, the parasitic fungus that controls insects, produces compounds that double cellular ATP production, ATP, essentially turbocharging the energy factories inside human cells. Early research suggests these compounds might reverse cellular aging processes that were thought to be irreversible. We're looking at a fungal pharmacy that could revolutionize medicine, providing treatments for conditions from Alzheimer's to cancer to depression. And unlike synthetic drugs, these compounds have been refined by millions of years of evolution, often producing fewer side effects than their artificial counterparts. But the most profound realization isn't about what fungi can do for us, it's about what they're offering to teach us about how to organize human society. The mycorrhizal networks that connect forest ecosystems operate on principles that put our economic and political systems to shame. They're decentralized. No single point of failure can bring down the entire network. They're resilient. They can lose huge portions of their infrastructure and continue functioning. They're regenerative. They constantly repair and improve themselves. Most importantly, they operate on principles of reciprocity rather than exploitation. Trees that contribute resources to the network receive support during difficult times. Those that try to take without giving get cut off from communal resources. It's a biological economy that has sustained life on Earth for hundreds of millions of years. Compare that to human systems that rely on centralized control, that collapse when critical nodes fail, that extract resources faster than they can be replenished, and that reward short-term profit over long-term sustainability. We've built civilizations on principles that fungi abandoned as ineffective millions of years ago. So here we stand, at what might be the most important crossroads in human history. Climate change is forcing rapid fungal evolution. Our technology is beginning to merge with their biological networks. Their chemical innovations are rewiring our consciousness and treating our diseases. We have an unprecedented opportunity for conscious collaboration with intelligences that have mastered the art of sustainable existence. The fungi have already chosen their path. In laboratory experiments, mycorrhizal networks preferentially support trees that feed them well, but they also provide emergency support to struggling trees that might not survive otherwise. They maintain the health of entire forest ecosystems because they understand that their own survival depends on the survival of their partners. They're offering humanity the same deal they offered plants 400 million years ago. Stop trying to dominate. Start learning to collaborate. Join the network. Contribute to the system. Benefit from billions of years of evolutionary wisdom about how to create sustainable abundance. The alternative is to continue our chemical warfare against organisms that have survived 5 mass extinction events. To hope that our 37-degree thermal advantage holds as the planet continues to warm. To gamble that beings who've had 1 billion years to prepare for this moment haven't anticipated our every move. Consider the evidence. Fungi aren't trying to destroy human civilization. They're offering to compost what doesn't work and feed what does. The pathogenic species that threaten us primarily target the sick, the old, the immunocompromised. The aggressive plant pathogens mainly attack monocultures, NDOD, the simplified, unsustainable agricultural systems that fungi may correctly identify as ecological mistakes. Meanwhile, the beneficial fungi are providing us with building materials that outperform concrete, computers that solve problems we can't, medicines that heal conditions we can't cure, and economic principles that create abundance without destruction. Maybe the message is simple. Work with us, or be composted by us. Join the network, or become nutrients for organisms that will. The choice is still ours, but not for much longer. The thermal barriers are falling as the planet warms. The chemical defenses are failing as fungi develop resistance. The environmental conditions are shifting rapidly in their favor, but we still have time to choose collaboration over competition, symbiosis over domination, integration over isolation. We can learn to build human systems modeled on fungal networks, decentralized, resilient, regenerative. We can accept fungi as partners rather than fighting them as enemies. The Wood Wide Web could become the blueprint for human organization. Imagine cities that operate like forest networks, sharing resources efficiently and sustainably. Imagine economies based on reciprocity rather than extraction. Imagine technologies that grow rather than being manufactured, that heal rather than pollute, that enhance natural systems rather than destroying them. The fungi have been offering these possibilities all along. They've been demonstrating sustainable abundance on a planetary scale for 1 billion years. We know how to create systems that last, that adapt, that thrive through change rather than being destroyed by it. Whether we're transformed or composted depends entirely on which category we choose to inhabit. The kingdom that rules from below has been patient beyond human comprehension. They've watched the rise and fall of countless species, survived catastrophes that ended entire eras of life on Earth, adapted to conditions that would challenge any other form of existence. They can wait a little longer for us to make our choice, but the evidence suggests they won't wait much longer. The spores are in the air, the networks are growing, the connections are being made. The most ancient intelligence on Earth is preparing for the next chapter of planetary history. The question isn't whether that chapter will be written. The question is whether humans will be characters in the story or just footnotes about a species that had potential but couldn't learn to collaborate. The fungal kingdom is ready. The networks are active. The invitation has been extended. How we respond will determine not just our survival, but what kind of survivors we become.